Hello everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Vestandria, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on dwarf planets and KBOs, fossils of solar system evolution. And after the presentations, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentations, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe study and for information on future webinars, please visit the Interstellar Probe study website. And now I'd like to introduce today's speakers. Dr. Kirby Runyon is a senior staff planetary geologist at APL and leads the Planetary and Optical Remote Sensing Working Group for the Interstellar Probe study. His research focuses on the photogeologic interpretation of landforms and processes on planets and small worlds across the solar system. Kirby is interested in planetary robotic exploration of trans-Neptunian region and the human exploration of the moon. Dr. Noemi Pinilla-Alonso is a planetary scientist at the Florida Space Institute with research interests in how our solar system formed and evolved to its present state. Her particular expertise is determining surface compositions of small bodies and interpreting them in terms of their surface altercation mechanisms and ultimately formation conditions. Of particular interest is investigating the distribution of volatiles, ices, organics, and silicate material in the solar system. She leads research efforts studying trans-Neptunian objects that started with her PhD dissertation on the surface composition of dwarf planets, and in particular, the Haumea family, and continues today as she co-leads a trans-Neptunian objects composition project that has guaranteed time on JWST. Additionally, since 2010, she has led the Primitive Asteroid Spectroscopic Survey, which is the most comprehensive spectroscopic study of primitive asteroids. The project has collected over 700 spectra of inner and outer belt objects and continues today with surveying the middle belt objects. Professor William McKinnon is a professor of Earth and Planetary Sciences and a member of the McDonald Center for the Space Sciences at Washington University in St. Louis. He is also a distinguished visiting scientist at Caltech's Jet Propulsion Laboratory. His research over the past 40+ years has focused on the structure, origin, evolution, tectonics, and bombardment histories of outer planet satellites and Kuiper Belt objects, and fundamentals of impact cratering throughout the solar system. He is presently deputy lead for geology, geophysics, and imaging for the New Horizons mission to Pluto and the Kuiper Belt, and is a science team member on both of ESA's upcoming Jupiter Icy Moon Explorer and NASA's Europa Clipper missions. He has served on numerous NASA and National Academies committees and review panels, and most recently was appointed to the steering committee of the Planetary Science Decadal Survey. He is a past chair of the Division of Planetary Sciences of the American Astronautical Society and past president of the American Geophysical Union Planetary Science Section, and is a fellow of the American Association for the Advancement of Science and the Geological Society of America. And now, Kirby, the virtual floor is yours.
Thank you very much, James. And I'm excited to kind of kick things off with a brief introduction because I want to get to Noemi and Bill's presentation as soon as possible. So if you'll go on to the next slide, please, James. Yeah, next slide again. We're just going to give a brief introduction. If you're new to the Interstellar Probe project, it's a mission concept we're developing. And its primary goal is to understand our habitable astrosphere. It's a heliophysics mission within the context of our interstellar neighborhood. And so the idea is to get out of the heliosphere and dip our toes in the waters of the galaxy on a mission that will be the first dedicated interstellar explorer. There's other opportunities besides heliophysics as well. Astrophysics can benefit from being outside the dusty zodiacal dust disk of our solar system, allowing for light to be less attenuated, light that's coming from the very first galaxies and the earliest stars, and a properly equipped Interstellar Probe could study that region of cosmic history in more detail. Of course, leaving the solar system, you're going to be flying by every planetary, or beyond the orbits at least, of every planetary object within a certain radius. And so there's huge opportunities for understanding the small planets and the planetesimals beyond Neptune. Now, Interstellar Probe is a pragmatic mission concept. We want all of the technology it would take to be available now or very near term to support a launch readiness date of 2030. Operationally, we want to be able to operate the spacecraft and communicate across those vast distances out to a distance of 1,000 astronomical units, powered by 600 watts from an RTG, over a lifetime of 50 years. Now, I do need to add the caveat that that the 1,000 AU and the 50 years are not meant to imply a 1,000 divided by 50 equals 20 AU per year speed. Those are decoupled constraints. So, but we want to be able to work at 1,000 AU and for 50 years. Next slide, please. I'm going to be focusing on the planetary science opportunities that can abound. Now, we know from the flybys of Triton, a moon of Neptune, by Voyager 2 in 1989, and the flybys of Pluto and its planet-sized moon Charon by New Horizons in 2015, that single flybys of planets can nevertheless be revolutionary. With the exception of some spectroscopic and rotational data, which is still important, all of our geological and geophysical knowledge of Triton, Pluto, and Charon, the only dwarf planets explored in the trans-Neptunian or Neptunian region to date, come from single flybys. And really, single spacecraft flybys are really the way to do outer solar system exploration beyond the orbit of Neptune or so, because you don't have to slow down to go into orbit. Yet, nevertheless, these fast flybys give us a wealth of geologic information. Next slide, please. And you'll see from this comparison of these three dwarf planets, Charon, Triton, and Pluto, just the incredible geologic diversity that we get from these single flybys. On Charon, in the upper left, we have geologic and geophysical evidence that a very short-lived hemispherical ocean froze and embayed or filled in the low areas for perhaps this foundering iceberg toward the top there. It then tectonically cracked and expanded as this icy dwarf planet froze. Moving over to the right to Triton, we have cliffs that are dominated by the sublimation of the bedrock of different volatile ices, perhaps nitrogen and methane, that have sublimated and caused cliff retreat. Towards the top of that image, you can also see a very European-like or Enceladin-like or Ganymedean-like double ridge that may be a spreading center. On Pluto, moving over to the right, we have terrains that are dominated by photolysis products of methane, tholin, that has snowed out of the atmosphere and covered a tectonically extended terrain. To the right, or to the east in this image, we have this nitrogen ice glacier, Sputnik Planitia, that seems to be convecting in the present day. Moving over to the right even, we see evidence for perhaps cryovolcanic constructs in this picture of Wright Mons, thought to be the result of cryovolcanic flows, cryolava, where perhaps there are slurries of methane and ammonia that get erupted to the surface. Of course, with imaging spectrometers, we can also look at the compositional distribution on the surfaces of these small planets, looking at the composition of, looking at the distribution, say, of nitrogen or carbon monoxide, carbon dioxide, water ice, methane, and other features. And taken together, geophysically and compositionally, we can infer that Pluto probably is an ocean world even now in the present day, despite being so small and being prone to losing its heat, in this wonderful image shown by planetary geophysicist and also space artist James Keane. Next slide, please. Of course, there are also planetesimals like Era. These Lego pieces are really building blocks of not just small planets like Pluto and Charon and Quaoar and Gong and others, but also the larger terrestrial planets and perhaps even the giant planets. And we can even look at the presence of things like methanol and other exotic ices on these planetary building blocks. And all of this from just single flybys, not going into orbit, but just flying quickly past, like New Horizons has done for Era. Next slide, please. Now, the great thing about dwarf planets is that there's so darn many of them. They're the most common, they're the most populous category of planet in our solar system, numbering at around 130 in the region beyond Neptune. And we count a dwarf planet as anything 400 kilometers in diameter and larger. That's likely large enough to be round by self-gravity. And that means that no matter which direction you want to send your spacecraft out of the solar system, with just a couple trajectory tweaks, you can probably fly by at least one of them. Now, of course, the Interstellar Probe mission concept is a is dominated by the heliophysics science constraints. And that community has really gravitated, if you'll excuse the pun, towards just off the nose, if you will, of the heliosphere. This is a plot of latitude and longitude, and leaving the heliosphere somewhere between the nose and a flank would allow for optimum heliophysics to be done. Now, if we're going in that direction, the planets Quaoar and Gong at distances between 30 and almost 90 AU from the sun, really about 45 to 90 AU from the sun, lie along that exit trajectory. And so either planet would be a very compelling target to begin to build up our catalog of understanding this most populous of planet category, the dwarf planets. Next slide, please. So some of the big pictures as we begin this nascent field of comparative planetology and ocean worlds beyond Neptune, we want to answer questions like, are there ongoing plumes or cryovolcanic or even tectonic activity on them? What are the variability of the landforms, the different compositions, different volatile contents of these dwarf planets? Tell us about the processes and evolutions. We also want to understand what fraction of them either had, maybe 4 billion years ago, or perhaps still do have liquid water in their subsurface. And how is that related to the window of habitability for these planets? We need to stop thinking perhaps of the habitable zone as only being that narrow strip around a star where liquid water can exist on the surface, and really extend that concept to where liquid water can extend below the surface. And this then dovetails nicely into understanding exoplanets, exo-dwarf planets, using the dwarf planets in our solar system as an analog for dwarf exoplanets, and again, understanding the habitability implications of those. Now, we have yet to discover any exo-dwarf planets, but I think we can be fairly sure that they're there, and hopefully one day we'll detect them. So that concludes my brief introduction, and I can't wait to see what Noemi and Bill are going to present to us next.
Thank you very much, Runyon, and sorry, Kirby. So I'm going to talk now about the fossils of the solar system, but I'm going to focus on the small bodies. My interest is the primitive icy surfaces, and I'm going to tell you now why studying the composition of these bodies is really interesting, and what the Interstellar Probe can do about that. Next slide, please. So, not because we have said it so much that these bodies are the fossils and that they help us understand the formation stages of the solar system. We have repeated it a lot, but not because of that it is less meaningful. So that's really true, because these objects their surfaces are formed by material that is substantially unaltered. But it's altered enough so that it's going to tell us about processes like irradiation, sublimation, formation of dust mantles, different things, different processes that affect these primitive bodies. And also studying their composition gives strong constraints to the dynamical studies that tell us not only how the solar system formed, but also how it has evolved to the actual solar system that we know up to today. The most intriguing materials that we like to trace in the solar system are the water in the form of water ice, or even in the form of hydrated materials that have OH components in their matrix. And also the complex organic compounds, because both of these are crucial to understand the origin of the life on Earth. Next slide, please. And this is all the information about our solar system. But also understanding our solar system and how it formed is going to give us crucial information to understand all of these exoplanetary systems that have been discovered and the circumstellar debris disks. Next slide, sorry. So what do I mean when I talk about small bodies? We typically, classically, have put them in what we thought they were, 3 different boxes. Next slide, please. So asteroids, we understand them as rocky, irregular bodies that orbit inside the orbit of Jupiter and that are inactive because they are rich on rocky materials. Then trans-Neptunian objects, we understand them also as inactive bodies, but in this case, they are in the form of like dirty ice snowballs. And then comets, these are the active bodies in the solar system, because they are formed of dust and gravel, but in a matrix of ice, and they come closer to the sun, what triggers sublimation and everything. So this was the classical understanding of the small bodies in the solar system. However, next slide, please. These lines, these different containers, are kind of blurred now by the knowledge that we have acquired in the last 15 or 20 years of studying all of these bodies. Next slide. Which are these tips that this knowledge that we have now that tell us that the lines are blurred? And I know these points are going to be kind of a tongue twister, but follow me and so that we go through it. First of all, we have the Jupiter Trans as the Hilda asteroids. Both are asteroids, but they orbit in resonances outside and in the Lagrange points of Jupiter outside the main belt. But we think now that they may be the link between the asteroids and the TNOs because of their composition, their colors, and their behavior. But also, if we go to the main belt, in the outer regions of the main belt, there are at least 2 asteroids that have been discovered that have water ice on their surface. How this is kept on their surface for their life suggests that there is sublimation and there is some kind of activity that keeps this thin mantle of ice on their surfaces. Also, we know now that there are asteroids, and by this I mean non-active rocky bodies that orbit in cometary orbits. So they come closer to the sun and they have different interactions with the giant planets. And also, we have asteroids that orbit in similar orbits as the rest of the asteroids, but that are active. And we have discovered up to now a kind of 10, 15 active asteroids, including the main belt asteroids. The mechanisms that track this activity we know is very diverse. So it goes from sublimation to total disruption of the nucleus, shredding materials, a lot of different mechanisms. And finally, we mentioned before that the TNOs were inactive icy bodies, but we know for sure that Pluto is active, and we know it way better now after New Horizons. I know Will is going to talk about that. So with all of this, I want to say that it looks like the distribution of the small bodies in the solar system and the diversity and their properties tell us that there is kind of a continuum and that there are interactions between and transient populations between what we first thought it was asteroids, comets, and TNOs. Next slide, please. And when it comes to the TNOs, that is what I'm most interested. We know it's a population that is not very well known up to now. Has not been so long from the discovery of the first trans-Neptunian object, that is not Pluto. And we have that these are all small bodies. And for small, we understand from tens of kilometers to some hundreds, and in some particular cases, even a couple of thousands. They all are orbiting far away from the sun, like about 40 astronomical units and beyond. And only the centaurs, that is a transient population, orbit in the region of the giant planets. So with being small, cold, and far, what we have is that the relative magnitude is small. So we have TNOs from 16 magnitude to 26. And that is very, very difficult to read from ground-based telescopes. We can go only beyond 20 magnitudes if we go to HST or very large telescopes, and that is only the population that we have covered in colors from the TNOs is really small. Let's go to the next slide, please. So what do we know from this small population that we have covered? Here on the right, you can see all the TNOs that we know the geometrical albedo. These were observed with the Herschel Space Observatory and with the Spitzer. And we know that they are kind of bright objects up to 30% of geometrical albedo. This means that they reflect 30% of the light that they receive from the sun, but also a lot of them are pretty dark. And only the large dwarf planets and the members of the Haumea family that appear there in purple and blue are bright objects. And we know that the diversity of colors of the surface that we think is related with the surface composition is large and is probably not related with the size of these bodies, except for the dwarf planets that are known now. Can we go to the next slide, please? And this slide is to introduce why we want to do a spectroscopy on these bodies and why is the most informative way to study them. So you can see on the very left of the screen reflectances of the materials that we think form the surface of the TNOs. And you can see that up to the K band, so up to 2 microns, only water ice and methane are very active. The other volatiles that could be on the surface of these bodies have very narrow absorptions, and the complex organics, like the tholins or the silicates, are just reddening materials that do not show any particular absorption band. But if we go to the wavelengths that the Spitzer covered, we have broader absorption bands that help us distinguish more what is on the surface of these bodies. And that is what shows the second plot there, like the regions dominated by the different materials, but still you can see that most of the TNOs that we know that are the black points fall in a region that there is a representation of a melange of these materials. There are very few TNOs dominated by methane or by water. Most of them are a mixture of organic silicates and ices. Can we go to the next slide, please? Here you can see the spectra in the visible on the image on the left and at the top of Iris, Makemake, and Pluto that are dominated by methane. So you can see that it's very informative because you have absorption bands. But if we go to objects dominated by water ice, the only thing that the visible tells us is that they are very neutral, so they don't absorb or reflect the light depending on the wavelength. We can see the water ice by the 2 strong absorption bands in the near infrared at 1.5 and 2.0 microns. If we go to a quasar that Kirby was talking about before, we have a combination of a red surface because of the color in the visible that absorbs more in the near ultraviolet, and water ice seen at 1.5 and 2 microns. But also this body is supposed to have methane and maybe hydrated ammonia that would be an indication of cryogenic mechanism. So understanding a surface like the one of quasar is a very interesting target. It's a very interesting question to do. Can we go to the next slide? This is what I think is going to be the next step in the study of TNOs. And it's what JWST is going to enable, and is to go farther from 2 microns where these absorption bands are way deeper and where we can distinguish better the material. In the left panel, you can see how good we could distinguish, these are theoretical models, how good we could distinguish a surface composed of silicates or dominated by silicates, a surface dominated by CH-rich organics, and a surface dominated by nitrogen-rich organics. And here on the right, you can see mixtures of materials. So if we have H2O, tholin, and pyroxene, you can see how much it absorbs above 2 microns. But then if we remove some of these components from the surface and we put another one, for example, the top one that has a tholin that is a nitrogen, then you have other different bands. So James Webb, when it flies, is going to give us a very good knowledge on what is on the surface of TNOs. Let's go to the next slide. This would be another point of interest, and I know that the Interstellar Probe has an ultraviolet photometer. So hydrated materials like hydrated silicates, but also CO2 and also water ice and also complex organics have distinct absorptions in the ultraviolet. So, and this cannot be done from ground base. So the knowledge that we have on this is based on some primitive asteroids or based on some icy moons of the giant planet. Can we go to the next slide? And I'm going to summarize here in 2 slides why I think Interstellar Probe can give a huge return if we turn the eyes a little bit to the TNOs. And it's because of the lack that we have on detailed knowledge on the surface of TNOs. We have some from general studies, but from ground-based telescopes, we don't have very detailed information. And if we could resolve elements on the surface, that would be great, because all of this surface composition is related also with physical processes, like I said before, with sublimation, with formation of dust mantles, with irradiation. So every piece of information that we could have would be a potential for breakthrough discovery. Near-infrared and ultraviolet are really interesting, and it would allow us to trace the OH components across the solar system, but also irradiation products as the complex organics, and all of this related to prebiotic material. The next slide, please. This is just some detail of kind of questions that we would like to answer about what is the recipe to cook a solar system and TNO, which amount of complex organic silicates and water ice we have, and what's the nature of this, and how much we can learn from that. And with this, I finish. Thank you.
Thank you very much, Dr. Pinilla-Alonso. And now for Professor McKinnon's talk.
Hi, everybody. Thank you to Noemi and to Kirby for the fascinating talks. I want to continue with the theme and examine the opportunities we have to explore these worlds of the trans-Neptunian region with the Interstellar Probe. Next slide. Now, just like Kirby mentioned, Interstellar Probe is a very ambitious mission. The idea is that to reach the heliopause, to pierce it, and to truly explore deep into true interstellar space, and to do it in an efficient way, that is to go faster than the machines that we have built and sent outward from the solar system so far. The point study being something like an SLS and with a Jupiter gravity assist. So you could actually reach hundreds of astronomical units over a mission that might last several decades. The opportunities for Kuiper Belt object or trans-Neptunian object more generally, science thereof is fantastic, because this machine, the Interstellar Probe, will be truly going where no probe has gone before, and will be carrying modern 21st century capable instrumentation. Next slide. Now, we've heard a lot about the Kuiper Belt already, or the trans-Neptunian region. I just want to just for a tiny bit of background, this is a slide I love. It's an unusual slide. It's not the usual XY plot. Known Kuiper Belt objects or trans-Neptunian objects are plotted according to their semi-major axis in terms of the distance from the origin at the lower left, and at the proper angle for the inclination of their orbit. And some of them have those lines that point down towards the origin. Those show you the excursions in heliocentric distance of an individual object, so from aphelion to perihelion. And this gives you a sense of the true global three-dimensional structure of the Kuiper Belt. And it's also color-coded by the interesting dynamical classes, which all have different stories to tell us. The teal objects are resonant with Neptune, such as Pluto, which you see there. Down near the x-axis in orange are these low inclination primitive worlds that we call the cold classical Kuiper Belt objects. And that's where Arakoth, which was originally called 2014 MU69, lives. And we've discovered thousands of these bodies telescopically, but this is just the tip of the iceberg. We estimate there are at least 100,000 worlds in the trans-Neptunian population that are larger than 100 kilometers in diameter. And we've begun to explore this region, as Kirby mentioned. Let's go to the next slide. So we passed through the Pluto system, and basically exploration of the Pluto system has revolutionized our understanding of planethood, because now we know what dwarf planets can be like. And Pluto turns out to be not just interesting geologically, there's just all sorts of the fantastic variety of geological things that are going on or have gone on its surface are quite apparent, and Kirby went through some of that, but it's an active body. The atmosphere of Pluto is active. The interaction of the atmosphere and the surface, the transfer of volatiles, sublimation and condensation is active. It's internally active. There's a great solid nitrogen ice sheet that is convecting in the solid state. That's up at the upper right there. We have evidence that there's geologically young, what we call cryovolcanism, which we don't truly understand. That's at the lower right. There's active glacier flow that we can see on Pluto, and there's evidence for glacial flow in the geologic past. So it's a fantastic planetary arena of activity. And as also was mentioned, the geological and geophysical inferences that we've developed point towards Pluto being an ocean world, that there is in fact a subsurface layer of liquid water. Next slide, please. But there are many known dwarf planet class worlds right now known in the Kuiper Belt. And here is a table of a bunch of them. There's not Pluto or its big moon. These are bodies that range from Pluto in size down to Charon, but is Pluto's moon in size. Most of them are known to have satellites. They probably all do. If you look at the right-hand column, you see different kinds of detected ices, detected spectrally, like Noemi was talking about. They're all different. The variety of geology we see on Pluto is different from the geology we see on Charon, which is different, if you like, from the geology we see on Triton, a captured KBO that orbits Neptune now. And I expect this level of diversity and complexity to be repeated as we make our way through exploring these other worlds. I don't expect them all to be active, but I certainly expect some of them to be active. They are truly not fossils. Of course, there are plenty of fossils because there are plenty of small bodies. Let's go to the next slide. After Pluto, the New Horizons mission passed by a cold classical Kuiper Belt object. And one of the things that we were really looking forward to was seeing a planetesimal, a planetary building block in its pristine state, because this is a part of the solar system where the bodies have not been broken up and reassembled by collisions like the asteroids have, nor have they suffered being roasted and toasted by sunlight like comet nuclei have. But what we saw there in terms of the shape and the organization and the composition and the lack of damage of these two separate lobes that form Arakoth has also revolutionized our understanding of planetesimal formation. That is, it is really pointed to and supports the modern theory of planetesimal formation, where in fact these individual bodies or lobes, like you see here, form from the collective instability of much smaller particles, which we like to call pebbles, in the presence, collective instabilities in the presence of solar nebula gas. So it's been absolutely, this mission has been fantastic, flying by two objects, incredible results just from the two flybys. And there are many more bodies out there, many of which we haven't discovered yet. Next slide. You know, we actually had to look carefully to find Arakoth. You see on the right, the mosaic of the search field that the Hubble Space Telescope used to actually find Arakoth for us. But we are on the threshold of a brand new era of KBO/TNO discovery. From space, the James Webb Space Telescope. From the ground, the Vera Rubin Large Synoptic Survey Telescope, both of which should see, if all goes well, their first light next year. And they'll be joined at mid-decade by the fantastic European Extremely Large Telescope with its fabulous 40-meter mirror. So the number and the characterization of KBOs and potential targets for Interstellar Probe is going to go up, up, up. So we're going out there with Interstellar Probe. What do you want to do? Next slide. There are a lot of instruments that you want to carry. It's a heliospheric mission, but the key instrument, the key technique to learning about trans-Neptunian worlds as you fly by is visible and near infrared imaging. And this has been the historical experience at Pluto and at Arakoth. You want to know what you're looking at. You want to know what size, shape. You want to know what the geology is doing. You want to know what's active and inactive. And you want to know what you're looking at compositionally. And that's where visible and near IR imaging comes into play. Next slide. But I want to make one thing very clear, and that is in order to carry this out in an effective manner, you have to target a targeted flyby, not a distant flyby. A targeted flyby is the gold standard. There is no substitute for proximity. Now, the speed that Interstellar Probe is moving will probably not be a problem, because we flew by tiny little Arakoth, only 35 kilometers long, at 14 kilometers a second, and we were able to manage to do that. But if you have a heliospheric mission, you're most likely, well, you're going to be a spinning spacecraft. So spinning is an issue. Now, there are different ways to ameliorate this. One, New Horizons, as an example, had the capability of switching from 3-axis stability to spinning. So Interstellar Probe could do that as well. But you might want to carry very long booms on interstellar probes and magnetometers and other instruments. You may even want to have things out on wire booms, at tens of meters away. This would be very difficult. There's no 3-axis in this case. But, maybe there's still a way to do it. So, spinning spacecraft like Juno images Jupiter not by targeting its imaging, but just scanning as it rotates with JunoCam. So maybe Interstellar Probe could do the same thing. Now, of course, then you won't get as much targeted information, and maybe it wouldn't be considered worthwhile, but that would have to be studied. Or another possibility is that you add some sort of gimbal or gimbaling to the foreoptics to enable pointing. But I don't know if that will really work with a spinning spacecraft. That's just something that has to be studied from an engineering point of view. There's also another possibility I'd like to raise, and that is actually trying to do those kind of observations separately with a daughter craft. But for that, let me get to my next slide before I say any more. In order to have a targeted flyby, you have to target. New Horizons devoted considerable optical navigation resources to refining its trajectory. You need to look ahead. Now, maybe this is less of, you might think shouldn't this be easy, but not necessarily. You can see where things are on the plane of the sky, but you don't know where they are in depth exactly. Maybe it's not such a problem if you're going to fly by a large body, a dwarf planet, but it's certainly necessary if you want to target and actually take the images when you think the body's there, if you're going to fly by a small KBO. And that brings up the other question, or the hidden question of hazard avoidance. Our mission, New Horizons, also devoted considerable resources to enable the close flybys of both Pluto and Arakoth, because you hit a small object, a grain of sand at high speed, and that, of course, Interstellar Probe is going even faster than we were. It could be a mission-ending kind of collision. Now, I have to say, this kind of worry goes all the way back to even the first asteroid encounter with Galileo passing by Gaspara. And so far, nothing has ever happened to passing by any sort of anybody. The only time we ever bump into anything is when we fly close to an active comet, which is erupting particles into space. Nevertheless, the Interstellar Probe has a long flight time and very ambitious goals. And would you ever entertain the risks to that entire mission by flying close to a KBO? So that's why I think trying to offload the risk and offload the targeting might make sense, let's say with a daughter craft. We fly daughter craft now. We've Rosetta had Philae, the Japanese Hayabusa 2 had several daughter craft that were dropped onto the asteroid Ryugu. I know you're going to say, oh, wait a second, I see those things. They have solar panels. Solar panels are useless in the Kuiper Belt. Well, Hayabusa 2 had one daughter craft, Mascot, which was battery powered and had a finite lifetime. And I think this is something worth studying that is a relative, not infinitely long lived, obviously, but a battery powered small daughter craft could, be separated at the appropriate time and follow a separate trajectory. It would then radio back it would carry out its primary observations of the KBO and send that information to the Interstellar Probe, which would then radio that back to the Earth. I don't know whether this is feasible, but we have ongoing developments in batteries, ongoing developments in CubeSats and NASA Simplex program. This thing, I think, could be usefully at least studied from an engineering point of view. But I don't want to leave on any kind of downer note. I just want to emphasize the opportunities in the Kuiper Belt or the trans-Neptunian region are fantastic. Let's go to the next slide. We've been to a resonant object. We've been to a cold classical, but there are bodies that we have no idea what they're like or even how they got there. These are a couple of more traditional graphs which show the eccentricities of Kuiper Belt objects as a function of, on the left, semi-major axis, and on the right, perihelion, or the closest point to the sun. The only point I want to make here is that there are bodies in that left graph whose semi-major axis are hundreds. In fact, one case, over 1,000 astronomical units. And on the right-hand side, their perihelia don't come anywhere close to Neptune, which is at around 30 AU. So we don't understand how these extreme scattered objects, as they're sometimes called, or detached objects, or as Scott Shepard likes to call them, inner Oort cloud objects, even got there. These are the true prizes, because Interstellar Probe will be going through this region of space and could rendezvous with one of these objects. And you might think, oh, there are just a few of them, but no, it's the tip of the iceberg. There are probably many, many of these extreme objects, and they're just waiting to be discovered. Next slide. This just gives you an illustration of what kind of orbits these are all real orbits. That dot in the center is the sun, and there's a little circle, that's the orbit of Neptune. All of these extreme objects spread out into heliocentric space in an incredible way, and we have no idea where the end of this is, where the edge of this is. Next slide. On the interest of time, I'm not going to go through this slide, but I'll just tell you, you might come back to it in the questions, that the technology, the engineering enterprise to have an interstellar probe will now give the human race the capability of doing other fantastic things. Anyway, and so I'll show you my final slide now. So just to summarize, the scientific opportunities for trans-Neptunian object science with an interstellar probe they're not just great, they're fantastic. But the pros and cons have to be carefully weighed against the interstellar probe's primary mission. And as Kirby said, it's a pragmatic, it's a real thing, not a fantasy. And that the primary mission is to study the outer heliosphere and interstellar space beyond. But I think if you step back from the whole thing, regardless, the combination of being able to travel to hundreds of astronomical units over many decades can catalyze new ways for people to think and to conceptualize their place in the universe. They're sort of expanding their sense of space, what it really means to be in the solar system, and also the timescale over which they might think about the future. That is, this combines what I like to call the big here with the long now. Anyway, thank you very much.
Thank you very much to all of our panelists. We're now going to have our question and answer session. And so I'm looking at the question and answer panel, and there's no questions at the moment, but please feel free to type your questions in now and we can start this session.
Well, James,
I see that we have a hand being raised too. Unfortunately, if you have a question, please type it in. Oh, okay. Thank you, Ed. So how long would the Jupiter flyby take? So the Interstellar Probe study is still a study that's being worked on right now. And so, we don't have an exact date for that, but perhaps I see that Pontus Brandt, our project scientist, just joined. So Pontus, would you like to take that question?
Sure, I can do that. So we're talking about a couple of hours. I think with the latest backup that we've looked at for with SLS and the kick stages, the transfer time to Jupiter would just be roughly under a year. So we're zipping, and then the flyby of the Jovian magnetosphere, if that's what you're interested in, we're talking less than 10 hours. So it's a very short time.
Thank you, Pontus. And the next question is from Ralph McNutt, and he says, hey, Bill, really nice talk. So what would be your current favorite target be if you were king?
Personally, it would be the dwarf planet Haumea, because we think that it's also suffered a catastrophic collision that has set it rotating very quickly and distorted it into a triaxial Jacobi-like shape. It has satellites, it has rings, it's got everything. It's not quite at the tip of the nose on the graph that Kirby showed, but it's not that far off. But it really seems to me that whatever we pass by will be revolutionary. I'm really not worried about what we pass by.
Thank you very much, Bill. And the next question is from Christopher Rose, and he asked, Dr. McKinnon, can you talk a bit more about what's on your penultimate slide means by, quote, catching a ride on an interstellar object? Has much work been done in this direction?
Let's go backwards if we can. I don't know if that's possible. or I could talk to it. Yeah, so if you look on the left there, you'll see the escape speeds of the 5 spacecraft that are leaving the solar system, some of which are still active, right? The 2 Voyagers and New Horizons. If you look on the pictures, you see our two recent interstellar visitors, Oumuamua and Borisov. And their V-infinities, their asymptotic velocities, are roughly double those escape speeds. One of the things I've noticed is that the Interstellar Probe, with the point study that's been, Pontus was just talking about, could bring them a capable spacecraft to a speed of, over 30 kilometers a second. So if we had advanced warning, and if Jupiter were in the right position for the proper gravity assist, like we were just talking about, then the same technology could allow us to launch a capable spacecraft to rendezvous with one of these interstellar visitors. And I don't just mean flying by, which, the Europeans have a Comet Interceptor, which could do something similar, but we would actually rendezvous and ride with it. We could even land on it. So that would be, I think, a mind-blowing spacecraft expedition. As to what work has been done on this, I don't think any work has been done specifically. People have been trying to imagine what I just mentioned, some sort of intercept mission with one of these objects. That's probably as much has been done.
Thank you very much, Bill. And the next question is for Noemi from Michael Paul. Is there a scientifically most interesting quadrant of the KBO region to visit from a solar system building blocks perspective?
So, let me know if I understood. You are asking if there is a region of the Kuiper Belt that is more interesting than other?
Yes, as in which region
yeah.
would you like to visit from the perspective of learning more about how the solar system was created?
Well, if we really want to go to very, very primitive, we think that the ones that have formed farther and stayed farther are the cold population of the TNOs. That has already been visited, we can say, with our report. But as Bill said, any of these objects would give us a lot of information, not only the cold population. I mean, the detached, the detached that spend so much time farther from the sun. So the radiation on the surface must have been different than, for example, for centaurs. So all of them are going to give us a lot of information.
Thank you very much, Noemi. And the next question is for Pontus Brandt, and is from Paul Sinek. How much flexibility do we have on outbound trajectory? Can we go anywhere in KB, either a node or the longitude of the ecliptic or whatever it's called?
Yeah, I can take this one. Thanks, Paul. So I'm trying to understand the question. So it's either picking a direction, as Kirby already pointed out. That is going to be dictated by heliophysics, by the heliophysics goal, of course. I think this other part or aspect of the question, are you asking if we could change direction once we have flown by a Kuiper Belt object? And the direct answer to that is no. You pick a direction in the sky and you go. And remember, our speed, as it was alluded to, will be right now in the study, we're getting something around 7.6 AU per year, which is roughly your 40 kilometers per second. So it takes a huge amount of fuel to even change direction by a few tenths of degrees.
Could I add to that?
Yes, please.
Yeah, so Paul, just like Pontus was saying, the direction will be chosen by the heliospheric community, and therefore something closer to the nose is the logical one. But in terms of engineering, depending on where Jupiter is, you could go in almost any direction in the ecliptic. If you want to get farther out of the ecliptic, as an example, I think you don't get as much a velocity boost. So that means a slower traverse, which may also not be desirable. But so if you wanted to reach Eris, for example.
Thank you very much, Bill and Pontus. And the next question is from Jose Gonzalez. If a path chosen bring the possibility of the flyby of 2 dwarf planets, what scientific criteria would be used to pick one? Pontus, do you want to take this one? Then we can also pass it to the other panelists if they like.
Let me read the question here. So I really think this is a question for either Bill or Noemi, actually. So yet again, I mean, the heliophysics goals will set a direction, and that's pretty sloppy. We're talking about 10 degrees or so for heliophysics. So within that cone, I believe there could be opportunities for that. But what would be the scientific criteria? Bill, perhaps maybe you want to take this one.
I think it's a question of opportunity. Once you have a general idea, if you want to pick something and what else is going to be along the trajectory, you won't have a lot of ability to steer. I would say that once we have a good census of what's sort of available along the trajectory, you can imagine saying, oh, if we do this, if we go in this direction, we can get 3 KBOs, or if we go in this direction, we'll get this one big one and one small one. It's kind of like picking a landing site on Mars. It's down in the details. But I suspect that the more objects you might be able to encounter just serendipitously or with small, I don't know how much trajectory, how much delta V the interstellar probe could apply to any kind of trajectory corrections.
Okay, thank you very much, Bill and Pontus. And Noemi, would you have a specific criteria that you would use to help select which 2 possible dwarf planets to look at?
I mean, it's not all about dwarf planets also. As Bill was saying, I think I would go with, if we pick one dwarf planet, what else can we do in this trajectory? Because also planetesimals and really small bodies give you a lot of information. And if you have to really, you are in that situation of picking between 2, I would go to what do we know of those 2 to see from which of them we can learn more. Because as Bill was saying, Haumeas is like 4 different dwarf planets, 4 different objects, because it's not only elongated, it has a family probably around product of a collision. It has a ring and it has satellites. So that would be a good one. But Eris also has satellites and is rich on methane. So how different is Eris from Pluto? Because they are in a very different orbit. Each of them is going to have a lot of different things to consider.
Thank you very much, Noemi, for adding to that. And for our last question today from Alan Stern, another way to beat the hazard concern Bill spoke of is to make a more distant flyby. This can be just as useful as a closer flyby if a much larger, for optics, say a 0.5 to 1 meter telescope is used for imaging and spectroscopy. Has this been considered? Pontus, do you want to take that one?
Sure. As usual, Alan, you have very perceptive questions here. The short answer to this is no, we have not really looked at that. The current model, we have 2 current example model payloads. So we have one heliophysics focused, and then we have one augmented payload. As an example, these are just notional payloads to drive 2 different mission architecture studies. And that augmented payload is considered a more closer flyby. So this is certainly a good suggestion that we will take a look at. Thank you.
It's also certainly true that a HiRISE-like instrument is much more massive, and you have to consider that.
Yeah, absolutely. Thank you very much, Pontus and Bill. All right, that's all the time we have for today. Thank you very much to all of our panelists, and thank you for attending today's webinar. The next webinar will be on Thursday, October 29th at noon Eastern Time on the extragalactic background light, opening a window to the early galaxy and star formation, where we will have a panel presentation by Casey Liss, Asantha Correa, and Michael Zemkov. Please visit the Interstellar Probe Study website for more information about the study and to view information on future webinars and events, including the 3rd Interstellar Probe Exploration Workshop. Also, please consider signing up for our listserv under the Community Involvement section of the website to make sure you're getting the latest information on upcoming webinars and events. Thanks for joining us and have a wonderful day.